We're heading into the last unit before your final exam. So this is the last group of stuff we have to learn. It's all about integrating, and integrating is the process of taking antiderivatives. So hopefully you did the best that you could with the Intro to Antiderivatives sheet. I didn't expect you to get them all right. Usually numbers 1, 2, 3, not too bad. Then people get to number 4 and it kind of throws them for a loop. Maybe you got it figured out. The e to the x is always the easiest. Sines and cosines, they just kind of flip-flop places. But as we go through, we'll be learning these things. So, antiderivatives. Taking a derivative and undoing it. It's like multiplication and division. Undo one another. Derivatives and antiderivatives. Undo one another. So we started earlier, we would talk about a position function. We take the derivative of it, we get a velocity function. Now we'll be able to start with the velocity function and figure out a position function from that. Or a biologist who knows the rate at which a bacteria population is growing might want to know the size of the population at some future date. So those are the kinds of questions we'll be able to answer. First, we start with a definition. A function capital F is called the antiderivative of lowercase f if on some interval the derivative of capital F is equal to lowercase f for all of the x's in the interval. Don't get hung up on the capital versus lowercase f's. We're not going to have a whole lot of notation to worry about with this section, this first section here. For instance, f of x is equal to x squared. Well, it's easy to figure out the antiderivative is 1/3 of x to the third power, because if you differentiate 1/3 of x to the third power, 3 falls down, cancels with that 1/3, you subtract 1 from the exponent, the derivative is x squared. But 1/3 x cubed plus 100 also has that same derivative. 1/3 x cubed plus 75 has the same derivative. 1/3 x cubed plus any darned number in the whole wide world has that same derivative. So the general antiderivative would be capital F of x plus a constant. So there's going to be lots of reminders. Don't forget to add your constant. Antiderivatives, it makes sense that we add c because all of these graphs here have derivative x squared because they are x cubed over 3 plus a constant. So let's try some examples. I need to find a pencil. So example 1. The most general antiderivative for f of x equals sine of x. So what has a derivative equal to the sine of x? Well, your first thought is cosine of x. But what is the derivative of cosine? It's negative sine. So the antiderivative of sine is negative cosine. And then we never ever, no not ever, forget to add c. And you can always check your answers. Yep, we got it. Part B, f of x is equal to 1 over x. So what function has a derivative equal to 1 over x? It's the natural log, and we put an absolute value in here because we can only take the natural log of positive things. So anytime you're taking the antiderivative of 1 over x, you need to throw an absolute value around the x. If we have x to the n power, and n is anything except -1, because -1, we just saw, is a special case. So think about the power rule for taking a derivative. Exponent falls down, divide by the new exponent. Subtract 1 from the exponent. I said that wrong. The differentiation rule is exponent falls down, subtract 1 from the exponent. So the antiderivative is add 1 to the exponent, divide by the new exponent. So x to the n plus 1 divided by n plus 1 plus a constant. Let's take the derivative of that since I did such a bang-up job explaining it. So we take the derivative of this function. N plus 1 falls down. Subtract 1 from n plus 1. Derivative of a constant is equal to 0. Cancel, cancel. X to the n power. Now, why doesn't this work if x is equal to -1? Well, if you have x to the -1 power, if you add 1 to the exponent, you get x to the 0 divided by the new 0. No, never. So, doesn't work. The special case is your natural log. And let's see. Here's the pretty answers. And it goes into more detail about the natural log function. Here's a table with some commonly seen antiderivatives. Let's make it bigger so we can see it. So if you have a constant times a function, its particular antiderivative, which is just the author's way of saying I'm not going to add c to these. So if you were doing an antiderivative, you would really, for the general one, you would add c. A constant times the function, and you can just have the constant times the antiderivative. The antiderivative of a sum is the sum of the antiderivatives. Here's the power rule that works unless the power is equal to -1, add 1 to the exponent, divide by the new exponent. Antiderivative 1 over x is natural log of absolute value of x. E to the x is e to the x is always e to the x. That's why we love e to the x. B to the x, when we took the derivative, we had to multiply by the natural log of the base. When we take the antiderivative, we have to divide by the natural log of the base. The antiderivative of cosine is sine. The antiderivative of sine is negative cosine. So the one that used to have a negative derivative has a positive antiderivative, and if they had a positive derivative, they have the negative antiderivative. Secant squared, the antiderivative is tangent because derivative of tangent is secant squared. And I should go ahead and just X out the hyperbolic ones. You don't need to know those. We haven't covered that. Let's look at example 2. I'm going to go ahead and write it down. It says that g primed of x is equal to 4 sine of x plus 2x to the 5th minus square root of x over x. Okay. Well, that constant rule up there tells me I'll be able to deal with this. There is no quotient rule for antiderivatives, but this is something that we can divide into two pieces. We did this when we first started doing derivatives too. Before we learned the quotient rule for derivatives, if we could divide it into pieces, we just divided it into pieces. I got 5 x's up top, 1 down below. So that's 2x to the 4th power. And I have x to the 1/2 up top and x down below. So this is x to the minus 1/2. Just because I'm likely to forget what my function was, it was 4 sine of x plus 2x to the 4th minus x to the minus 1/2. So my antiderivative, the antiderivative of sine is negative cosine. 2 hangs out. Add 1 to the exponent. Divide by the new exponent. Add 1 to the exponent. Divide by the new exponent. Never ever forget to add c. I'm okay if you want to leave it like that. If you're offended by the fact that you have a fraction in the denominator of a fraction, you can rewrite it as 2 instead of 1/2. Doesn't matter. Okay.